This program is brought to you by Emory University.
The Old Kingdom, approximately 2707 to 2170 BC, marks the first period of sustained cultural and economic prosperity in ancient Egypt. It is during the Old Kingdom that the Djoser Step Pyramid, the pyramids at Giza, and the Sphinx were constructed. Broad colors have been depicted in ancient Egyptian funerary art since the Old Kingdom, and are pieces of jewelry worn by the gods, pharaoh, and non-royals alike. Broad color beads were often made from faience. Faience is a self-glazing ceramic made by combining sand or crushed quartz, lime, soda, and/or potash, and metal compounds for color. Water is added and the mixture is shaped to form an object. The finished object is air-dried, and metal salts migrate to the surface through evaporation. Then, the object is fired, causing the metal compounds to fuse and create a glassy, colorful surface layer. Here are images of the Leipzig broad collar and choker before restringing. The broad collar and choker were discovered by Steindorf between 1903 and 1907 in an expedition to the Giza West Field, and are dated to 2613 through 2181 BC. The broad collar and choker were discovered in the stone mastaba of Wehemka, a royal acquaintance and scribe, and his wife. By comparing this stringing to other examples of broad collars and chokers, it is clear that the stringing is inaccurate. The current colors of the beads are beige with light green and a dull purple. The pendants are darker, but similar in color to the purple beads and have patches of aqua. The color of the beads lacks the vibrancy that is associated with faience, and the beads would have been more colorful originally. Color loss is not unique to these beads, and has been observed in other examples of Old Kingdom beads as well. In most inorganic materials, color is contributed by transition metals. Elemental analysis indicated which metals are present in the Old Kingdom faience beads. We used a handheld X-ray fluorescence spectrometer, referred to as XRF for short, to analyze the Old Kingdom beads. XRF is a surface analysis technique that can generally detect elements with atomic weights greater than neon, in a concentration greater than 1 part per million. To understand XRF spectroscopy, recall that electromagnetic radiation has wave-like properties and can be described by energy, wavelength, and frequency in the formula E equals hc over lambda, where h is Planck's constant, c is the speed of light and is also constant, and lambda is the wavelength. The wavelength is the distance between two peaks in a wave. Frequency is related to the wavelength by frequency equals the speed of light over the wavelength, and corresponds to the time it takes for the following peak to reach the same position as the peak that is preceding it. By examining the formulas more closely, it becomes apparent that long wavelengths correspond to low frequencies, and also smaller energy values. XRF instruments emit an X-ray in the direction of the sample. Because X-rays are high energy, they can cause an electron to be removed from the inner shells of the metal atoms. Electrons are removed most readily when the energy of the incoming X-ray is slightly higher than the ionization energy of that electron. Removing an electron from a shell increases the energy of the atom and makes the atom unstable, so an electron from an outer shell replaces the displaced electron. When the outer electron moves to a lower shell, to replace the removed electron, it loses energy because of the Coulombic attraction between the electron and the nucleus. It is this emitted energy that is measured by the XRF detector. The emitted energy is also an X-ray, though a lower energy X-ray than the initial beam. The innermost shell of an atom, the s orbital, contains 2 electrons and is called the k shell. The p orbitals are called L shells, and the d orbitals are called M shells. When an electron is removed from the k shell and replaced by an electron from a higher energy shell, this produces what is called a K-line in an XRF spectrum. When an electron is removed from the L shell and replaced by an electron in the M shell, this is called an L-line. The K-lines are typically the strongest peaks. Multiple peaks occur because atoms at room temperature are not all in the ground state. XRF can distinguish elements because the spacing of the shells is unique for atoms of each element. Electron-electron repulsion and shielding of the inner shells from the outer shells contribute to the distances between the shells. The number of electrons in each shell differs between elements. Therefore, the electron-electron repulsion and the effect of shielding also differs between the elements. However, XRF cannot distinguish between isotopes or ions of an element. XRF detected calcium, sodium, chlorine, sulfur, potassium, aluminum, magnesium, iron, and copper in both colors of the beads and pendants. The pendants also contained zinc and lead. Only the purple beads contained manganese. Copper, manganese, iron, zinc, and lead are elements that are commonly associated with color. The other elements that were detected correspond to the bulk components of the Faience mixture, or impurities. Copper-based compounds were the most common colorants in the Old Kingdom, corresponding to shades of blue and green. The original color of the light green beads was likely a blue-green. The purple beads contain both copper and manganese. Manganese generally produces a purple color. The addition of manganese and copper would likely result in a dark blue color for the beads. With better understanding of the beads' original colors, we could begin restringing the Old Kingdom broad collar. The first step was to carefully take apart the previous stringing and sort the beads by shape, size, and color. In consultation with the curators of Egyptian art, the beads were arranged in rows. In order to complete the restringing, faux beads were fabricated out of polymer clay. The blue-green and dark blue colors were slightly exaggerated in the new beads to help the modern viewer distinguish the color pattern and better imagine the broad collar's original appearance. This image depicts a Photoshop colorization of the broad collar. The colorization is an approximation of the original color of the beads. Here is an image of the final result after the restringing.
The preceding program is copyrighted by Emory University.